Now we are looking at multivariate regression. We saw last week developments for linear regression and polynomial regression also in 1D. Now we will see the same kind of developments, but for multivariate case. So we are looking at multivariate linear regression functions, where we have as x measurements over d variables. So our function try to predict RT, and this RT we try to fit is a real value. And so we have a function h that is function of w0, w1 up to wd, plus some epsilon here, which is describing the noise. And so as such, using a linear model, so another one model, we have w0 plus w1 x1t, w2 x2t up to wd x dt plus the epsilon. So we are assuming that the noise is a white noise center at 0. So this epsilon is following a Gaussian distribution center at 0 with a noise level described by a sigma square. So basically, higher the sigma, more important is the noise in that sample. And now what we are looking for is to minimize the quadratic error. So it's basically equivalent to the maximum likelihood as we saw last week. So minimizing the quadratic error is like finding out the maximum likelihood estimation of that. And we are looking to get the error of the parameters W0 up to WD given the dataset we have at n. And so the point is to minimize the difference between the values we try to predict. So this is the kind of ground truth or the target values versus this is the h, basically minus the hx. So minus the prediction made with the linear model we are using for regression. And all is squared because we are using the quadratic error here. So from that, we are computing the partial derivatives of this error function. So we are taking this equation, compute the derivative according to W0, W1, W2 up to WD, and that gives us the solution. We are making this equal to 0. We are solving the equation and so on. But it can be tedious. It's not necessarily like this formulation is correct, but it's not directly usable or easy to use on a computer. We can get into something better by defining what we call the normal equations for multivariate regression. So basically, it's to define this set of equations. It's the same thing. It's basically based on the partial derivatives. We are able to obtain these equations, and these equations, are relatively regular. So from that, we are able to define this thing. We are able to define a matrix version of that. So this is really the starting point, the result of getting the partial derivatives of our equation using a x that is described that way, a w described that way, and a r described that way. We are able to restate this thing as that thing. And this is the new matrix version of the normal equations we can use for that. And okay, what we want here is in fact to isolate the w. The w are the weights that we want to learn. So how to obtain these w's is simply to multiply by x transpose x inverse of all this times x transpose r. So making this computation give us the w value to use. And this w value will minimize the quadratic error. So some notes on that. With the normal equations, we are dealing with polynomial of order 1. This is basically the linear model. Usually in multivariate cases with many dimensions, this is good enough. We are rarely going with higher order polynomials, except for really low Ds, like in 2, 3Ds, maybe we can develop this, but for like 10, 50 Ds, 50 dimensions, we are not looking at something different than this linear model. It doesn't really make sense, or at least it is kind of really complex. This is not something we are looking for. Another interesting thing to look at is that looking at the W values, we have W0, 1, 2 up to WD. We know that the WI gives the importance of the variable xi. So for example, when we see that the absolute value is kind of low, it means that the variable is not that useful for making the regression, for predicting the value. So we can, if we know that the range of the variables are comparable, so we know that they are working in about the same range. If we are looking at the absolute values of the W's, we can rank them accordingly, and we can see the variables that are the most useful for making the predictions. And possibly we can remove the variables which have a really low value. So the sign of WI gave us an idea of the effect of the variable xi. So if the sign is negative, it means that when the variable increases, the effect on the forecasting or prediction is we get predicted lower values. And conversely, when the sign is positive, it's really that the variable and the prediction are varying in the same way. When we are looking for predicting like as output values, not a real value, but a vector. So for example, we don't want to predict like a single real, but we want to predict 5 values as a vector. We simply have to, we can simply do a multivariate regression, linear regression on each of these predictions, each of these targets independently. We don't have to mix them. For this model, we just have to have like, compute 5 different set of weights, one for each target, and that's it. That is working. That is dealing well with this kind of task.